I've been getting a lot of requests recently to do a follow-up video on my simple algorithm video and actually take a look at the piezo algorithm, because these two really are the main two pressure velocity coupling algorithms that you see in a lot of CFD codes. And I'm really excited to bring this video to you actually, because looking through the internet and the various sources I could find, often the difference between the two algorithms is quite confusing. It's not very clear what the real difference is between them, beyond simple is often used for steady state flows and piezo algorithms often used for transient flows. So what I've done here is I've really dug into the equations and actually managed to work out what the difference is in the loops between the equations, and I'm really excited to bring this video to you. I really think you're going to enjoy it and finally really understand what the difference is between the two algorithms. So yeah, sit back, take some notes. It's quite a long video because we've got a lot of equations and background to go through, but I know you're going to find it extremely useful. So just to start things off with a background and a reminder of all of the pieces of the algorithm that you'll need to know and remember, and then after we've been through the background, I'll go in and look at the actual solution process that the algorithms use. So just a reminder of where we start. For an incompressible flow situation, we have the continuity equation, equation 1, and the momentum equations there in equation 2. And for this simple system, what we can see is that we've got 4 equations. That's the continuity equation and 3 momentum equations, and we've got 4 unknowns: pressure, ux, uy, and uz. 4 equations and 4 unknowns, so that means we can find a solution. However, if we just look at those equations, the first thing we notice is that there's no equation for pressure. So that's the first problem in the pressure velocity coupling problem. Now, for a compressible flow, we'd have an equation of state like the ideal gas law, and we could use that to calculate pressure. But for incompressible flow systems, for example, if we have water, then we can't use that to calculate the pressure. And the second problem which we have here in the incompressible Navier-Stokes system is that the continuity equation there, equation 1, is really a restriction on the velocity field that we compute. So the way you should really think about this system is if you solve the momentum equations, equation 2, you'll get a ux, a uy, and a uz, and those components together have to satisfy the continuity equation to be a valid solution. So you can't just take any solution of equation 2. The solution has to be specific and has to satisfy the continuity equation. So really, for the incompressible system, the continuity equation is a restriction on the solution that we compute. And so this is what's often called the pressure velocity coupling problem, and the piezo algorithm and the simple algorithm are 2 algorithms that we can use for incompressible flows to deal with this problem. Now, when thinking about how we solve this problem, the first thing we need to do is think of things in matrix form rather than in differential form, which we saw there in the previous slide. And the first step we can do is write the momentum equations in general matrix form. And you see that there in equation 3. We've got a matrix of coefficients m multiplied by the unknown velocity vector u, and then that's equal to negative of the pressure gradient there on the right hand side. And how do we perform this discretization? Well, we do that usually using the finite volume method, and I've got other videos on this channel detailing the finite volume method, or if you want to see things in more detail, you can look at the various courses that I have available, and that will show you how to get that matrix of coefficients m there. But generally, when we're thinking of pressure velocity coupling problems, we want to be thinking of things in matrix form. So we've got an mu is equal to minus the pressure gradient there on the right hand side. And so that's a reminder of what those terms mean. Now, it's also worth remembering that the matrix of coefficients m, all of those coefficients are known, and we calculate those and know what they are, depending on what sort of discretization schemes we use for the convection term, the diffusion term, and so on. And I've got other videos on this channel about how you discretize the individual terms. But for now, we want to be confident that we're just starting with that general matrix equation, mu is equal to minus the pressure gradient there. Now, at this stage in our pressure velocity coupling problem, what we could do is take the pressure and the pressure gradient from the previous iteration or the initial condition, and then we could just solve that equation directly. So we know the matrix of coefficients m, and we know the source term on the right hand side from our initial guess or previous iteration, and that would allow us to compute a velocity vector, or the momentum field u. Now, because this is the pressure velocity coupling problem, it's worth noticing that when we solve that momentum equation, the velocity vector u there does not satisfy the continuity equation. As a reminder, remember, the vector u, v and w has to satisfy the continuity equation for it to be a valid solution. So at this stage, when we solve the momentum equation, this is often called a momentum predictor in the algorithm. And it's a prediction because we've got a guess for the velocity field, and it doesn't currently satisfy the continuity equation. Now, a small side note for those of you who use OpenFOAM and like to dive in and actually look at the equations in the source term, in the source code, you'll often see this momentum predictor stage written as you can see there at the bottom of the slide. You're clearly solving a momentum equation, and that's equal to a source term, which is the pressure gradient there on the right hand side. Now, when we're analysing and looking at these algorithms, there are a few other extra stages which we need to think about, which will help us when we analyse the system and look at how the pressure velocity coupling algorithms are put together. And the first stage in all of these is, if we think of that matrix of coefficients m there, what we can do is extract the diagonal from that matrix. And the diagonal component of the M matrix is known, and I'm going to use the notation A there, the A matrix. And you can see there it's just extracting those coefficients of the diagonal and using that to make a new matrix. Now, if you follow along with the various sources in the literature, you may see this written as A sub P instead of capital A, which I'm using here. I prefer to use capital A just as a reminder, this is a matrix, just like everything else. Whereas if we used an AP, we could confuse that with a value. So from the M matrix, we can extract the diagonal if we want. And why would we do that? What can we do with this A matrix? Well, the thing to remember is that with a diagonal matrix, it's very easy to compute the inverse of the matrix. And the inverse of a diagonal matrix is just 1 divided by each of the diagonal coefficients there, which you can see in equation 7. And for those of you who follow along the sources in the literature, you will often see this written as 1 over AP. So again, 1 over AP, it's just the same as the inverse of this A matrix, but I prefer to call it the inverse because it's more correct and it reminds us what we're actually doing. And again, if you follow along in OpenFOAM, you'll often see this 1 over AP written as you can see there in an extract from the source code, which is sometimes called RUA, which means the reciprocal of the A component there from the U equation. So now that we've extracted the diagonal from the M matrix, we can do a bit of manipulation. And with that manipulation, we'll see another matrix called the H matrix appear, which you'll often see if you look through the sources in the literature. So if we think back to our momentum predictor equation, which we have there in equation 8, instead of mu, we're going to write that as au minus h. Now A, as a reminder, is that diagonal matrix that we extracted from the M matrix, and then the H matrix, which you can see there, is just the residual of all the stuff that we've got left. So we extracted the diagonal, and then all the stuff that's left, we're going to bundle that together and call that the H matrix. So the reason I'm using H, it may seem random at this point. Why is he choosing H? What does it mean? Well, H is often the notation used by OpenFOAM and sources in the literature if you follow along. So I'm deliberately using H here so that you know exactly what it means. Now, there's a small tripping point here, which you could easily make the mistake if you're not careful, and that's notice that we're using the decomposition in equation 9 there. So mu is going to be au minus h and not the decomposition which you can see there in equation 10. So what do I mean by that specifically? Well, if you think of the M matrix, if you just took the M matrix and stripped out the diagonal, then the remainder of that specific matrix you could call H, and that would be equation 10 there. So that would be all of the off-diagonal components and then zeros along the diagonal, and that's specifically not what we're going to do there. And the reason that we don't perform that decomposition, equation 10, is we want to be able to rearrange this equation for u, and that's going to be multiplying by the inverse of the A matrix there. So if you thought about multiplying equation 9 there by the inverse of the A matrix, you could rearrange for u. However, if we used equation 10 and multiplied by the inverse of the A matrix, we wouldn't be able to rearrange easily to get that U vector there. So we're deliberately using equation 9 there for the decomposition. And that's very important to remember, but it's often skipped over if you look at a lot of the sources in the literature. So this is just a note of we are rearranging that M matrix, the matrix of coefficients, multiplied by the velocity vector. That's going to give us AU minus H. It's the main decomposition here in the algorithm. The rest follows relatively straightforwardly, so you may want to take a few minutes just to go over that point in your heads. So now that we've got that decomposition, that's equation 11, MU, we're going to replace by AU minus H, and we could just rearrange that to get things in terms of H. And a reminder here that H is just the residual that we're getting after performing this decomposition. And why do we care about the H matrix? Well, the H matrix allows us to calculate the source term for the pressure equation. So we are going to use the H matrix, don't worry. If you've seen my video for the simple algorithm, you will have seen this matrix appear before. But I just wanted to line things up for you first to say, where's this matrix coming from and what does it mean? It's the residual that's left after we strip out those diagonal coefficients from the M matrix. So, as a reminder, we've got the momentum predictor. We've solved the momentum predictor to get some kind of velocity field. And what we now need to do is we need to have a way of calculating the pressure. And the way we do that is by deriving a pressure equation. And again, if you've seen my video on the simple algorithm, this is just repetition and you'll remember how this appears. So if we start with equation 13 there, that's we've got AU minus H on the left-hand side, and then minus the pressure gradient on the right-hand side. That's the momentum equation as before. And then the key step is to multiply by the inverse of the A matrix, as we showed before. And of course, the inverse of the A matrix is easy to calculate because it's diagonal. And if we multiply everything by the inverse of the A matrix, we get an expression there in equation 14 for the velocity. And you can see the velocity there is A inverse multiplied by that H matrix minus A inverse times the pressure gradient. Now, just think about what we've done here. All that we've done is rearrange the momentum equation to get to equation 14, and that's an expression for the velocity field. But if we want to get an equation for pressure, what we can do is substitute equation 14 into the continuity equation. So up until this point, the continuity equation has just been a restriction on the velocity field that we compute. So we've computed the velocity field and it would have to satisfy the continuity equation to be valid. But now what we're doing is we're actually going to use the continuity equation to derive a new equation for pressure that we can solve instead. So instead of having a restriction, we now have an equation that we can solve, and that's much easier. So if we substitute equation 14 into the continuity equation, we arrive at equation 15 there. And what you'll see straight away is that the unknown is the pressure there, P. On the left-hand side, we've got the Laplacian, or Nabla squared, of the pressure, and then on the right-hand side, we've got a source term, which is A inverse multiplied by the H matrix. So this is just a reminder, this is all background so far for setting up these algorithms. We've got a momentum predictor that we can use to calculate a velocity field, and now we've also got an equation for pressure. And using those together, we can come up with an algorithm for solving the momentum and pressure equations together, while ensuring that the velocity field satisfies the continuity equation. So now that I've got this pressure equation, I just want to highlight for you, for a few of you who might be following along either using sources in the literature or by actually digging through the OpenFOAM or other CFD code, you'll see this pressure equation sometimes written, as you'll see there in equation 16, we've got 1 over AP instead of the inverse of the A matrix, they're the same thing. And some people use H of U instead of just H as it is, to calculate that residual matrix on the right hand side. I personally just prefer to use H because I feel like with the extra U it can get confusing there. And in OpenFOAM you'll often see the fragments scattered through the code at various places looking like this. We've got that first expression for the inverse of the A matrix. The second expression there is an expression for the H matrix multiplied by the inverse of the A matrix, and then right at the bottom there you can see an expression for the Laplacian of the pressure. So that's the pressure equation that we would be solving. And on the right hand side, you've got a divergence term for the h by a term on the right hand side. So if you're looking through the source code or various sources in the literature, when you see these things recognized as a or h or Laplacian of the pressure gradient, you'll understand now where they're coming from, and you can follow the derivation that I've just given there if you want to derive it for yourself. But now let's actually go ahead and look at the algorithms so you can see how the simple and piezo algorithms actually solve the system together. And what I'm going to do is call these pressure velocity coupling algorithms because they're specific for incompressible flows when we have a pressure velocity coupling problem. So in the algorithms, the first thing that we always do is solve the momentum predictor first, and that's equation 17. We know the matrix of coefficients m, and we have an initial guess or the previous iteration of the pressure term on the right hand side, and we solve that for the velocity field. And the velocity field is a guess as before. The reason it's a guess or it's a prediction is because it doesn't yet satisfy the continuity equation. But now that we have the velocity field u, a guess, we can calculate the H matrix. That's equation 18. So we can see there on the right hand side, the H matrix actually depends on the velocity field, and we've got the A matrix there, which we strip out from the M matrix. So momentum predictor first, and then we jump straight in to calculate the H matrix. And the reason we calculate the H matrix is because the H matrix is a source term on the right hand side of the pressure equation. And that step, I think, is sometimes missed out by some of the explanations which you may see on the internet. So now we can solve the pressure equation, and on the right hand side there you can see the H matrix, which we've just calculated, and the inverse of the A matrix, which we stripped out from the M matrix. And solving equation 19 gets us the pressure field, and once we have the pressure field, we can then use equation 20 to compute a new velocity field. Now the difference here when we calculate the velocity field is that the velocity field here is calculated explicitly. We're not solving a matrix equation, we're calculating it directly from the A matrix, the H matrix, and the new pressure matrix, which we just calculated there in equation 19. And this is called an explicit pressure correction. And what it means is the velocity field that we compute here will satisfy the continuity equation. So it's, you might say it's a solenoidal vector field, but it satisfies the continuity equation. And this is exactly what we want. This is the corrected velocity field at the end of the algorithm. And for some of your interest, this is why, for example, the simple algorithm is called the semi-implicit method. The semi-implicit means that it's partly explicit, and the explicit part is equation 20 there, where you're explicitly calculating the velocity field directly from the pressure field that you've just calculated. However, there's a small problem here, and that is, if we think back to the pressure equation, equation 21, on the right hand side the source term has got the H matrix in there, and what we know is that the H matrix depends on the velocity field u, which you can see there in equation 22. Now originally we used the momentum predictor to calculate that H matrix, but now what we've done is we've corrected the velocity field, so u is different now to what it was before. And of course what that means is that if u is different, H is different. So the source term in the pressure equation there, equation 21, has changed. So what that means is that the pressure field is no longer correct. And even though our velocity field satisfies the continuity equation, our pressure field is not correct and it needs updating. And maybe take a few minutes to think that over, and if you just write the equations out for yourself, you'll see that actually the pressure equation is no longer correct, and we need some way of updating this H matrix so that we can resolve the pressure equation. And this is the key point to where the simple and the piezo algorithms come in. And this is often not explained very well on the internet and in other sources, where people talk about relaxation factors and time steps and things and often get confused. But really this is the key step. It's how do we go back and update the pressure equation by updating that H matrix there. And the two algorithms are really two different methods of updating the H matrix. And I'm going to start with the simple algorithm because it's easier, and then I'll show you the piezo algorithm after, which is a different way of updating the H matrix and the pressure equation. So the simple algorithm is very direct, and what it says is Well, we need to update the H matrix, so I'll just go all the way back to the start and solve the momentum predictor again. And so I just go back through the entire loop. And for those of you who might be finding that difficult to follow in your heads, like I was, I find it much easier to actually just write down the equations and just look at them and see where are we updating. So a reminder of what the loop will look like for the simple algorithm: we start with equation 23, we solve the momentum predictor. Once we have u, the velocity field, we calculate h, which is equation 24. Then we calculate the pressure field by solving the pressure equation there in 25, and then we update the velocity field there in equation 26. But now what we do to correct the H matrix is go all the way back to the start of the loop, equation 23, solve the momentum predictor again, and use that to update the H matrix so that we can then solve the pressure equation again. And it's worth noting sometimes when you look through these algorithms that this loop is often called an outer corrector loop. And the reason it's an outer corrector loop is with the simple algorithm, we're going all the way back to the start of the process and solving the momentum predictor again. So really it's a very direct way of doing things, and it uses quite a long loop. The Piso algorithm is slightly different, which we'll see in a minute. But hopefully by writing those equations down, you can really see exactly where the loop is in the simple algorithm. And it's worth noting so far that I haven't said anything about time stepping or relaxation or convergence or anything. This is just the stages and the equations that you would solve if you were using the simple algorithm for your pressure velocity coupling. So what about the Piso algorithm? Well, in the Piso algorithm, what we do is we solve the momentum predictor once. So we start with equation 27 and solve that once directly. But then what we do, as before, we calculate the H matrix and use that to solve the pressure equation, equation 29. And then once the pressure equation's been solved, we correct the velocity field there using equation 30. But the difference between the Piso algorithm and the simple algorithm is that rather than going all the way back to the start there and solving equation 27, we jump straight back to equation 28. So you can see equation 28 there. To compute the A matrix, we need the velocity field. And rather than use the velocity field from the momentum predictor, we're going to use the velocity field directly from the one that was just corrected there in equation 30. And so you can see that actually now we're looping over equation 28, 29, and 30. And we only solved the momentum predictor once. So this loop is a lot tighter. We're only looping over 3 equations. And this process is often called an inner loop if you look at CFD manuals and in source codes. So actually, at a fundamental level, the difference between the Piso algorithm and the simple algorithm is very slight, and it's just which way we're updating the loop there. Now, it's worth, now that we've looked at what the difference is between the two algorithms in the order that the equations are solved, now what I'm going to do is introduce some of the other concepts and reasons why you might choose to use a simple coupling or a Piso coupling depending on your simulation. Now, the first place to start is really to think historically about these algorithms and where they came from and what they were originally proposed for, because that will usually help you to decide which one you'd like to use. And the simple algorithm was proposed first in the 1970s, and the simple algorithm was originally intended for steady state flows. Now, originally intended doesn't necessarily mean you'd have to use it for a steady state flow, but it was originally intended for steady state flows. And just a reminder, with steady state flows, what that means is we don't have a time derivative. So that expression you can see there in equation 31, the du dt, does not exist for a steady state flow. And what does this mean for the equations that we're solving? Well, if we think about a transient flow where we have a very small time step, then if you look on the right hand side of equation 31, the up divided by delta t is going to get very big. As the time step gets very small, up over delta t gets very large. So if we think of this in terms of the overall matrices that we're constructing, the du dt term gets a lot bigger as our time step gets a lot smaller. And what that means is if we think of all of the terms in the equation, we have time derivatives, we have convection, diffusion, gravity, forces, and source terms, then the time derivative there is becoming dominant. It's becoming a lot larger than the other terms. And what you'll see there if you look is that we've got a u sub p, and that usually in CFD terms means that the term is on the diagonal of the matrix. So the UP over delta T occupies the diagonal of that M matrix. And as delta T gets very small, that means that the diagonal of the matrix gets very big. And for those of you who think back to your linear algebra or look on the internet for general concepts in linear algebra, as the diagonal of that matrix gets a lot bigger, the system tends to get more diagonally dominant, and that's the phrase that's often used. But what it means in practice is that the equations get more stable. They're easier to solve, they take less iterations to solve. And so what does that mean? It means generally, for a transient flow, the matrices that we construct are more stable, take less iterations to solve, and are less likely to diverge. And the simple algorithm was not intended for these flows. The simple algorithm was intended for cases when the matrices don't have the time derivative and they're more likely to be unstable. And what the simple algorithm does in those instances is we use under relaxation. And in this instance, under relaxation is used to artificially increase the size of that diagonal term. Because we don't have a du dt, we need to make something else instead so that we can inflate that diagonal on the matrix to make it more stable. So if you were just thinking about this intuitively, you may think that a transient flow would be easier to solve than a steady state flow, but actually steady state flows tend to be a lot more unstable. It's just that transient flows take many more iterations to solve because of the time stepping. So it's a bit counterintuitive. So in the simple algorithm, and when it was originally proposed, under relaxation is often employed. And so if you use the simple algorithm yourself, you will often see under relaxation in the equations, whereas you may not see them if you've got a transient flow. Now, this under relaxation is slightly different to a traditional under relaxation, which you may be used to from general algorithms. And the way I'm going to explain this to you is by starting with equation 32 there. And you can see you've got APUP, that's going to be the diagonal terms in the matrix, and then you've got the off diagonal terms in the summation there, ANUN is equal to a right hand side matrix. So equation 32 is basically just a general form of a linear algebra matrix equation there. And when we apply under relaxation to the momentum equations, what we're going to do is add in two additional terms there. And you can see these terms in red in equation 33. We've got a 1 minus alpha over alpha multiplied by APUP. So the APUP is going to sit on the diagonal of the matrix. And alpha is going to be the under relaxation factor, which is always between 0 and 1. And what we've done is we've added that term to the left and the right hand sides. On the left hand side, we've got the current value, but on the right hand side, we've got the old value of the velocity field. And the reason we can add this to both sides of the equation is that when the equations are converged, u old will equal u new, and these red terms will cancel out and disappear. But until we get to that point, those terms are going to be different, and they're actually going to help us to converge the matrices. So if we look at the left-hand side of equation 33, we can actually group those first two terms together, and then we arrive at equation 34. And you can see that the equation that's got an under bracket there is now scaled by 1 over alpha. And that is the diagonal of the M matrix. So AP again being those diagonal terms, but they're now multiplied by 1 over alpha. And because alpha is between 0 and 1, if we make alpha a lot smaller, we're going to artificially inflate that diagonal and make the diagonal a lot bigger in comparison with the other terms. And that's typically what we would get with time stepping. So we can see that this is totally artificial. We've just manipulated that diagonal to make it bigger, and this will make the equations more stable when we're solving them in a steady state form. So this is the premise of under relaxation that the simple algorithm typically uses. And it's worth comparing this with the traditional way to do under relaxation, where if we had a value that we'd calculated in an algorithm, we could update that using something like equation 35, where we add on a fraction of the new value to the old value when updating the field. And this form of under relaxing the fields, so pressure, turbulent kinetic energy, temperature, is often applied to pressure, turbulent kinetic energy, and temperature, but the matrices themselves are under relaxed in the momentum equations. And to be honest, I'm not too clear with why that process happens. It's not very clear from reading through the literature. However, for you, when you go through and if you look at it, be aware that there are actually two different types of relaxation. One different type that's applied to the momentum equations, that's increasing the strength of the diagonal there, and then we've also got direct relaxation of the fields, pressure, turbulent kinetic energy, and temperature. So this under relaxation is typically applied to the in the simple algorithm. However, the piezo algorithm is different. Now, the piezo algorithm was introduced slightly later than the simple algorithm. Historically, it was introduced in about 1986, and it was originally intended for unsteady, incompressible flows. So again, for the unsteady flows, we do have a time derivative, so that diagonal in the matrix, the M matrix there, is a lot larger, and the system is more diagonally dominant. So we don't actually need under relaxation, on the condition that our time step is very small. So if we have a very small time step and our current number is less than 1, we can actually get away without any under relaxation at all. And this is how the piezo algorithm was originally proposed. So if you look through any source code on piezo algorithm and piezo loops, you'll often not find any under relaxation at all. And that's because it's assumed that the current number is very small and we're using very small time steps. Now, why was the piezo algorithm introduced and what was it for? Why couldn't we just use the simple algorithm? You know, we could take our first time step and fully converge that time step using the simple algorithm and then just step on to the next time step. Well, if we think about it, then actually with the simple algorithm, we often need a lot of iterations to fully converge when we apply it. And common practice tends to be we need a few thousand iterations, often 5,000, to fully converge a steady state flow with the simple algorithm. But if we have an unsteady flow, we're going to have to do a lot of time steps, and so doing 5,000 iterations every time step tends to be really inefficient, and we often won't be able to get a full solution. And so the piezo algorithm is deliberately a lot shorter than the simple algorithm. We do one momentum predictor and then often two inner loops of the pressure corrector there, and that's often fairly sufficient to converge the time steps after we've proceeded over the initial transient in our simulation. So this is why the piezo algorithm was introduced. It was introduced after the simple algorithm, and the reason for it was we can't afford to do 5,000 iterations of the simple algorithm every time step. We need something that's shorter and quicker and will allow us to rapidly push through the time steps. Now, there are of course more modern pressure velocity coupling algorithms which you may have heard of, and some of these will tend to try and do even better than the simple and piezo algorithms. So one such example would be the Pimple algorithm, which you may have heard of in OpenFOAM, where you can actually use larger time steps and then converge the time steps partially, maybe doing 15 or 20 iterations within a time step, but allowing you to extend the current number greater than 1. But I'm not really going to look at those algorithms here. I just wanted to focus on the simple and piezo algorithms. Now, one thing I want to finally touch on before finishing it are the non-orthogonal correctors, because if you're looking through the source code, you may see these correctors as well, and it's useful to know what the difference is between an inner corrector, an outer corrector, and a non-orthogonal corrector. So when understanding non-orthogonal correctors, the first thing to do is to look at the pressure equation, which you can see there in equation 38. Now, notice that the pressure equation is essentially a Laplacian, or more technically a Poisson type equation, where you've got nabla squared times the pressure is equal to some source term on the right hand side. And of course, if the mesh is not orthogonal, that means this equation needs to be solved several times in a row, updating the source term each time to account for the non-orthogonality. And for those of you who haven't come across this before, it's worth going and looking at my video on non-orthogonal correctors to understand why this is needed for meshes that aren't perfect squares. So as soon as the mesh is not perfect squares, you have to include non-orthogonal correctors, or at least consider them if you're going to get an accurate answer. And so how do these non-orthogonal correctors appear in the simple or piezo algorithm when we're thinking about it? Well, what we do is that we iterate the pressure equation directly in a row with the number of non-orthogonal correctors that we want to use. Now, at the moment, this might be a bit overwhelming for you. You might think there's a lot of equations going on and I can't quite remember which equation comes where and how many times do I need to loop it. So what I've done here is I'm just going to go through a quick example of what the sequence of equations will look like if you have non-orthogonal correctors in a simple algorithm and non-orthogonal correctors in a Piso algorithm. So you can actually see and start to think through which equations are being solved and when. Now, the first example here is a simple algorithm, and in this instance we're going to have two non-orthogonal correctors. And just a reminder of how the algorithm works, we start with the momentum predictor there, equation 39, and once we've solved that, we calculate the H matrix as normal there in equation 40. And what we would then do, now that we've got the H matrix, is we can get the right-hand side of the pressure equation there in equation 41. We've got H and we've got the inverse of the A matrix. So we can solve the pressure equation. But now, because we are doing non-orthogonal correctors, we continue to solve that pressure equation immediately. So in this instance, we have two non-orthogonal correctors, so we end up solving the pressure equation 3 times in a row there, 41, 42, and 43. And once we've done the non-orthogonal correctors, we then go on to proceed with the algorithm as we normally would. So for simple, we would correct the velocity field there using equation 44, so it satisfies the continuity equation. And then, because this is the simple algorithm, we loop all the way back to the start there and go back to equation 39. And we would continue to loop through these equations until we were converged. So if you took out equation 42 and 43, that would just be the normal simple algorithm. All that we're doing with the non-orthogonal correctors is just directly solving the pressure equation again immediately with an updated source term to account for the non-orthogonality. So what about the Piso algorithm? Very similar. The first thing we'll do is we solve the momentum predictor, equation 45. Now remember, with the Piso algorithm, we only solve the momentum predictor once in each loop. So then what we do is we dive into the inner loop and we calculate the H matrix. Once we've got H, we can solve the pressure equation there, equation 47, as we have the right-hand side. Now with two non-orthogonal correctors, we would just repeat the pressure equation again immediately and go equation 48, 49. Those are our two non-orthogonal corrector loops, and then we can finally correct the velocity field there in equation 50. Once we have that, we can use it to update the H matrix and then again go back into that pressure equation, because remember, with the Piso algorithm, we use the corrected velocity field there, equation 50, to update the H matrix rather than the momentum predictor, which is what we would do if we were using the simple algorithm. So hopefully, just through those last two examples, it might be a bit easier for you to follow of which equation am I solving in what order and what's the difference between the Piso and the simple loops in the process that we use to solve them. So just wrapping up with a summary of what we talked about here and a few reminder points for you. All pressure velocity coupling algorithms, whether that's Piso, simple, or another one which you may see in the literature, will solve a momentum predictor first. So we're going to be solving mu is equal to minus the pressure gradient. All of the algorithms will solve that. And then what we'll do is we'll move on to solve a Poisson equation for pressure and use that solution to update the velocity field so that it satisfies the continuity restriction. Now at this point, what we need to do is update the source term in the pressure equation and solve it again. And the difference between the simple and the Piso algorithms comes into how we update the source term, that H matrix. We either do that by looping all the way back to the start and solving the simple algorithm again, or by going directly back and using the momentum field that was just corrected to satisfy the continuity equation. So there it is, that's the end of the video. I hope you guys enjoyed that and found it as useful as I did going through it. It's really useful to actually finally see what the difference is in the loops between the two algorithms. So let me know what you think. Did you enjoy the video? Did you find it useful? I know I was getting a lot of requests to do a video on the Piso algorithm, and let me know in the comment section below what you guys thought. Are there any other really pressing videos that you think I should have a go at? Because there are still many different areas of CFD which aren't covered at all well, and I'm slowly trying to get through the big topics one by one so that we can finally build up a picture of how all the aspects of the modern CFD codes finally work. So thanks a lot for your support again, guys, and I'll see you soon.